Hello, I'm Brandon with Experience Anatomy. Today we're going to do a rundown of the digestive system. We have a variety of mediums here to explore the complexities of the gut. So as you sit on your couch following a hearty meal, you can ponder the wondrous science occurring in your abdomen. Digestion is going to begin in the oral cavity. First up, though, we have two different types of digestion. We have physical and chemical digestion. Mastication or chewing is an example of physical digestion, while digestion carried out by enzymes is classified as chemical digestion. When mechanoreceptors and taste receptors sense that food is present in the oral cavity, they're going to send signals to the salivary glands of the body. There's three pairs of those. We have the parotid gland, which is just anterior to your ear. We have our submandibular glands, which are just next to the angle of the mandible. And then we have our sublingual glands, which lie beneath the tongue. Saliva is mostly composed of water and some ions, and it also has two enzymes it releases, salivary amylase and lingual lipase. Amylases break down carbohydrates and lipases break down fats. So salivary amylase is going to kickstart starch digestion for us, while lingual lipase is rather ineffective and true fat digestion won't really begin till we get deeper down the line. Now we need to get this chewed up food into the gut somehow. This is accomplished by the swallowing reflex. This can be broken up into three phases: the oral phase, the pharyngeal phase, and the esophageal phase. The oral phase has to do with the formation of a bolus. As we chew and move food around our oral cavity, we create this clump of food that we call a bolus. The oral phase is just the voluntary movement of the tongue, moving that bolus of food to the back of the oral cavity, getting it ready for swallowing. The second phase is the pharyngeal phase, and it is the involuntary activation of pharyngeal muscles, which aids in the transit of that bolus to the esophagus. Two very important things are going to happen during that phase. The first of which is the soft palate is going to swing up and block entry into the nasopharynx. The second of which is the epiglottis is going to sling down and block access to the trachea. So I've essentially cut off access to my respiratory cavities, ensuring that food goes down the correct piping. Hopefully it does. Finally, we have the esophageal phase. Once food enters the esophagus via the upper esophageal sphincter, it is moved down the tube via peristalsis. Peristalsis is the wave-like contractions that move food along the digestive tract via local stretching and flexing of the digestive wall. So we're just milking it down the chain, essentially. The bolus then reaches the lower esophageal sphincter, which then relaxes, allowing the contents to enter the stomach. The stomach is where digestion starts to really take off. First, the muscular layers of the stomach's wall are going to act in concert to swish the contents of the stomach back and forth, a process we call mixing waves. This is an example of physical digestion. The stomach also has a really neat physical attribute. Its inner wall has a lot of folds thrown into it called rugae. These allow for consumption and filling of the stomach without stretch of the outer wall. So it's akin to like a sheet on your bed with all the folds and undulations on it. If you were to tighten it out, you could tighten it out without stretching the mattress beneath it. Next up, we have the gastric glands. These secrete many compounds crucial to digestion, but we're going to focus on the two main players, hydrochloric acid and pepsinogen. HCl, or hydrochloric acid, is secreted by the parietal cells of the stomach. This creates an acidic environment which serves to denature or unfold any proteins that we have ingested. Denatured proteins are much easier for enzymes to work with. Pepsinogen is an inactive protein-cleaving enzyme that's released by the chief cells of the gastric glands. It is activated in acidic environments, so once it reaches the cavity of the stomach, it becomes pepsin, where it can now act out its protein cleaving function. The pancreas is well known for its endocrine function, which is maintaining proper blood glucose levels through use of hormones insulin and glucagon, but it also has a profound impact on digestion. The acinar cells of the pancreas secrete a wide array of macromolecule digesting enzymes. We've got pancreatic amylase for carbs, pancreatic lipase for fats, multiple inactive protein cleaving enzymes, and even some nucleases to break down any animal or plant DNA that's entered the diet. Like pepsinogen in the stomach, the protein cleaving enzymes of the pancreas are released in their inactive form. This is done to ensure they don't break down any cells of the organ itself and just break down the proteins of our diet. Molecules that require activation to perform their function are called zymogens. The pancreas also secretes a lot of bicarbonate ions. This serves to neutralize the acidic conditions that the stomach squirts into the duodenum, as it's not really built for the acidic environment that the stomach is. All of the pancreatic juices are going to travel through the main pancreatic duct, which is essentially just a hallway that runs through the pancreas. The main pancreatic duct is going to join with the common bile duct from the liver and gallbladder. That junction point is a swelling, and that swelling is called the ampulla of Vater. At the end of the ampulla of Vater is the sphincter of Oddi, which is essentially just a door that separates the duodenum from the pancreas. Once food enters the duodenum, or once the duodenal wall stretches, that sends a signal to the sphincter of Oddi to relax, thus releasing all of those pancreatic enzymes as well as the bile into the duodenum, so all of those macromolecules start to get broken up and we can start getting some nutrients out of the diet. The gallbladder serves as a storage and concentration center for excess bile created by the liver. Bile acts as an emulsifier, which means it breaks down large fat droplets into smaller drops that enzymes like lipases can more adequately handle. When food is sensed in the duodenum, the gallbladder is signaled to contract, which sends the bile down to the ampulla of Vater so it may aid in the digestive processes. The small intestine is the site of nutrient absorption, so it has physical attributes that expedite that process. Remember, form always follows function. The intestinal wall has circular folds thrown into it called plicae circulares, which help to swirl the food paste around, allowing it to contact as much intestinal wall as possible. Furthermore, these cells of the intestinal wall have finger-like projections called villi on their apical surfaces. The villi also have finger-like projections called microvilli, so just imagine fingers coming out of my fingertips. All of these attributes have a common theme, though, and that is the increasing of surface area. In biology, if you're increasing surface area, that usually means something physiologically important is happening there. In this case, that's nutrient absorption, which is extremely physiologically important. Moving on to the chemical side of things, the small intestine contains many brush border enzymes. These are going to carry out the last step of macromolecule breakdown. So we have things like maltase, sucrase, and lactase, which are disaccharide cleaving enzymes, and they're going to yield their respective monosaccharides, which are the building blocks of carbs. So, for example, sucrase is going to turn sucrose, the disaccharide, into glucose and fructose, its respective monosaccharides. Then we have peptidases, which yield amino acids, which are the functional building blocks of proteins. And we have some lipases yielding the fatty acid chains and glycerol backbones, which are the functional components of fats. So all of these are then absorbed into the blood, except for fats. The constituent parts of fats are reassembled into something called a chylomicron, which is essentially a transporter for fat-soluble items. These are too large to be absorbed into the capillaries, so they are instead absorbed into the lymphatic system through a lacteal. This means they essentially bypass the portal system and enter the blood, where the thoracic duct of the lymphatic system joins back with the venous system, which is at the junction of the left internal jugular vein and the left subclavian vein. So very interesting that it bypasses the portal system, and all those fats pretty much just go right to the superior vena cava. Finally, the large intestine serves mostly just to pack the feces. It is composed of the cecum, the appendix, the ascending colon, the transverse colon, the descending colon, and the sigmoid colon. It performs minor water absorption, as most of that happen in the small intestine, and it can also absorb simple molecules and vitamins, but it's essentially just a transit point, as a lot of that science has already been accomplished. I hope that this improved your understanding of the wonderful complexity that follows every meal. If you have any questions, please feel free to comment down below, and I will try to answer to the best of my ability and to the best of what I feel I'm qualified to comment on. If this helped you out, please do leave a like, and if you think it would help someone else out who is interested in the study of the body, please don't hesitate to share it with them. Thank you so much for your time, and have a wonderful day.